All right, guys, moving into the second part of Chapter 11, we are now moving on to what we call three-dimensional solids. In this particular textbook, everything we've done up until this point in Chapter 11 has been two-dimensional figures, where we've been finding area. And in every geometry book I've taught out of prior to this one, they've separated 2D and 3D solids into two different chapters. This book decided to put them all together. So let's get into three-dimensional solids. We're going to just try to introduce some vocabulary here today, and the first word is a strange one you probably haven't heard before. That word is called polyhedron. And hopefully you guys recognize some of the parts of this word here. The prefix poly always means many. And when we get to hedron, I kind of focus on those three letters right there, which kind of looks like it spells the word head. That makes me think of a face on the front of a head. So a polyhedron is essentially a many-faced object. So our formal definition right here, a polyhedron is a three-dimensional solid made up of many, there's the polygon faces. So what I have then on the rest of this slide here, guys, are just a series of polyhedra. That would be the plural of polyhedron with an A at the end. And this is what some of them can look like. And we're going to define these in a little bit greater detail here in a minute. So I'm not going to spend too much time talking about each one of them. But I wonder if, as you guys look at them, you might recognize some of these shapes as things that maybe you've dealt with in your everyday life. I would say probably, well, not probably, definitely the most common of all of them is the cube right here in the middle here. And most commonly, you'd see a cube when you play a board game like Monopoly and you throw a pair of dice. Each one of those, called a die individually, is a cube. But some of you guys play some weird games out there, Dungeons and Dragons, different role-playing games, whatever. You sometimes see some dice that are different shapes. So I have seen octahedron dice right there. And if you recognize the prefix oct right there, an octahedron is actually going to have 8 faces. This one right here, an icosahedron, that is something that has 20 faces. So I've seen some really interesting dice that look like that. Dodecahedron, that one, like dodecagon, is going to have 12 faces. So there's a lot of weird things that are out there. When we get into shapes that look like, let me switch colors on you here, that look like this tetrahedron right here or this guy, we end up talking about something called pyramids, which is a word everybody knows fairly well, but we'll get into greater detail here in a second about what that means. But all of these figures, looks like 3, 6, 8 of them drawn here, meet this definition right here for polyhedron. Three-dimensional solids, meaning that they've got a little bit of width to them. They run front and back. They've got left and right. They've got a little height to them. They run up and down, but they also have some depth to them. They run front and back, which is hard to demonstrate here on an iPad, but that's what we mean by a three-dimensional solid. And I think I had one more picture at the bottom of this thing, and yeah, that would be, I think that might actually be the icosahedron that we were looking at right there. Okay, so let's break it down now, and let's get into the two specific types of polyhedra that we're going to talk about the most. The first, guys, we want to make sure we get this definition in our notes right here, is a prism. And the definition of a prism here is going to be this: a three-dimensional solid with two congruent and parallel polygon bases. So that's pretty important. Congruent and parallel polygon bases, and they're connected by rectangular lateral faces. So that's the important definition we need to get down for a prism there. And I was going to go ahead and draw one, but you know what? That's what this next slide is for. So I just wanted to take a minute and draw a couple of examples of what some of these prisms might look like. And you'll notice each time I talk about a prism, there's an adjective that comes in front of it. A triangular prism, rectangular prism, and hexagonal prism. These would just be 3 of the ones that we can draw, but there's actually an infinite number. Now I want to begin with the one in the middle because rectangular prisms are the ones that we see the most. Anytime you buy something from a store or get shipped to your house from Amazon that comes in a box, 99% of the time that box is a rectangular prism. So a lot of you guys probably know how to draw this already. There's lots of different ways you can do it, but probably the simplest way to draw a rectangular prism is to begin with a rectangle here, 4 sides, 4 right angles, and I don't necessarily want to make it a square prism, so I'll make the base and the height different quantities right here. And then probably the best thing to do is from any one of those 4 corners, I'm going to start here in the upper left, we're going to draw a little diagonal piece that's heading to the back. back looking something like that. And now, the important thing is we want to draw basically that same segment three more times. Here would be another one, and I'm drawing this one here, I hope you notice, congruent and parallel to the piece that I just drew. Let's do it another time, should get us right about there. And if you know where I'm going with this, the one that I'm about to draw, guys, right here, should be a dotted line. You'll see why in just a second. And now I'll go ahead and connect those 4 points that I have now on the back of this figure with that line segment there, another one here, and now this one will be dashed or dotted, and same thing with this one right over here. And the key to those dotted lines, everybody, those are hidden lines that are in the back of the figure that we would not be able to see if this thing was a solid. So that's what we mean by a rectangular prism. Now, if we go back to our notes here, a prism is a three-dimensional solid with two congruent and parallel polygon bases that are on opposite ends of the figure. So probably the easiest way to think about this would be to say, okay, let me go to blue here, guys, that my base of this prism is going to be a rectangle that's located right here on the bottom of the figure. So I'll go ahead and shade that in. Now, if that's my base, then there would have to be a congruent and parallel rectangle on the opposite side of that figure. And sure enough, there's another one right up here on the top that would look like this. So this will work here, guys. Those two rectangles that I've shaded in blue, those are our bases. And then the height is the space in between right there. So basically, this is a base up here on top. This is a congruent and parallel base on the bottom. And the height then, we'll define this more in the next section, is the distance between your two bases. Okay, so that's what we mean by a rectangular prism. Now, let me draw a couple more for you here, but hopefully we're going to get the hang of it. Now, with a triangular prism, I'm going to draw this one a little bit differently, and you'll see why in a moment. I'm going to draw a triangle that's going to look like it's obtuse, kind of drawing it on a skewed axis right there, okay? So there's my triangle. And now, just like I did on the last problem right here, from one of the vertices of the triangle, I'm going to draw this little slanted line segment here that's going to look something like that. And that piece that I just drew is the key. I'm now going to draw that two more times, congruent and parallel, hopefully, to what I just drew. So there's one, and the third one would come from this vertex of the triangle, but that one is going to be dotted because it's going to be on the back end of the figure. And now I have these 3 points right here. They all need to be connected with line segments as well. This one would be hidden, so would this one right here, but that one didn't draw that well. That one we would be able to see. So that should look probably something like that. And that's a decent drawing right there of a triangular prism. Now, the difference between what I would expect a middle schooler to be able to tell me and a high school geometry student to be able to tell me is this. When we hear the word base, we all instinctively think that base has to be on the bottom and that height always needs to run vertically, as this one did. But if I go back to my definition here, a prism is a three-dimensional solid with two congruent and parallel polygon bases. In this case, a middle schooler, don't put this in your notes, guys, might tell me that this rectangle on the bottom is the base. But the issue then is there's no rectangle up here on the top of the figure that's congruent and parallel to that rectangle that I just drew. So my mistake here was thinking that the base has to be on the bottom. When you're trying to identify bases, you look for congruent figures that run parallel to each other. And I've got that here with this one triangle that's kind of on the front of this wedge shape, and then there's another one right there on the back. So hopefully you see the connection now between this diagram and the one here in the middle. So in this case, okay, this triangle is one of the bases. This triangle here is the other base. And the height now is the distance between those two bases. So it's actually running horizontally in this case. Again, a middle schooler is going to tell me that height always needs to run up and down, but that's not the case. Height is the distance between the bases. And if we wanted to do a hexagonal prism, not as bad as you might think. The bases here are going to be hexagons. So I think here I'm going to draw, now I'm going to draw this kind of skinny and funny, and you'll see why here in a minute, but okay, this is going to be one hexagon. There you go, 6 sides. And now I'm just going to draw everything shooting off to the right like this. So there's one, that's what we call a lateral edge, and here comes a second one, congruent and parallel. Here's a third one right about there, and a fourth one that would get me to roughly there. And once we get to these two, they're going to be a little bit harder to see. They'll be on the back of that figure, looking something like that. And now we'll go ahead and connect those 6 points that we just came up with line segments. 1, 2, 3. This one will be dotted. So will the fifth one. And so will the 6th one right there. So not a great diagram there, but that is a hexagonal prism, kind of like a drum being held sideways. So where are my bases? The 2 congruent and parallel figures. So we've got a hexagon on the left, a hexagon on the right that's supposed to be congruent and parallel to that one. I didn't do a great job drawing it. And height is the distance between those bases. So in this case, your height is running horizontally from left to right. Here's one base, and here's the other base. Okay, so all 3 of those are examples of prisms, but those are not all of the prisms that are out there. You could make a pentagonal prism, an octagonal prism. You're just naming it according to what shape its base is. So that, everybody, is what a prism looks like. And that's the first major type of polyhedron that we're going to be talking about here in 11.4. The second type is coming next right here, and that is a pyramid. So our definition for pyramid is going to be similar here, but with a couple of big differences. It is again a 3-dimensional solid, but this one, a pyramid, only has 1 polygon base. A prism had 2, and this one has what we call triangular lateral faces. So that's the definition of a pyramid. 1 base, it can be any kind of polygon you want it to be, and triangular lateral faces. I didn't really talk about this, and I should have here a second ago. In all of these prisms that we just drew, I didn't really focus on the fact that, I'm going to switch colors here, guys, and I'm going to go green here. This comment right over here, that every prism has 2 congruent and parallel polygon bases, but the lateral faces, the sides, are rectangles. Well, sure enough here, guys, you've got a rectangle here, another rectangle right here. There's 2. This gets messy. There's a rectangle on the back of this figure. That's 3. And a rectangle over on the left side of this figure. That's 4. And in all of these prisms, you see rectangles here that are connecting the 2 bases. There's one. This is a rectangle right over here. So is this guy right there. Yeah, so prisms always have rectangles that connect the 2 bases. But when we get to pyramids, now we're going to see triangles that's connecting the base to the vertex up on top of the pyramid. Let me show you what I mean here. I'm going to switch back to blue. And let's talk about this. Again, these are just 3 of the pyramids we could draw, but there's really an unlimited number. Let me start again in the middle with square pyramid. And these would be kind of like the great pyramids that you see in Egypt, everybody. So if you think you have a sense for what a pyramid is, and it's based on that idea, this is probably what you're thinking of. A square pyramid has a base that's a square, but what you can't do is just draw a square that looks like a square and then just make a point up here, because this is not really ever how a pyramid looks. That's pretty awful. When you look at something from a slanted perspective, everybody, that square doesn't really look like a square. What it ends up looking like is more of a rhombus. Okay, maybe something like this, and that would be parallel to the bottom side, and that would be parallel to the other. Now again, if that's a square, all 4 of these sides should be congruent to each other, and those should be right angles, even though they don't look like it. All right, but when you look at a right angle from a funny perspective, right angles often don't look like right angles. Now, let me get back to where I was a second ago, because I've already done something I'm not going to like here in a minute. Oh boy, I guess I lost all of that. Okay, what I should have done is drawn this line to be solid, this line here to be solid, but then this one should have been a dotted line, and so should this one right here. Again, you'll see why in a second. Now, to find the peak of the pyramid, what you really want to do is visualize a diagonal coming across this square and try to find the midpoint of that diagonal right there. And then you want to go straight up from that point, guys. So if I were to visualize, go straight up from that red dot, and let me just put a big fat dot right here. And that is what we call the vertex of our pyramid. Now, when I get done, I might want to erase some of that. Now we're going to draw some line segments that connect the vertex to the four corners of our square base. So there would be one of them. That would be solid. You'd be able to see that. Here's another one right there. A third one takes us off to the right. You'd be able to see that. But this fourth one that goes to this point here, that is going to end up being a dotted line because you won't be able to see that. All right, guys, there's some extra junk in the middle right there, but that's a square pyramid, and its base is the square that this whole thing is sitting on. Okay, so that's what we've got right there for what a pyramid looks like. Now, just a little bit of vocab. You've got this square base down here on the bottom. I wouldn't put this in your notes yet. We'll talk about this later. But this segment that comes straight down to the center right there is called the height or the altitude of your pyramid. And that goes right down the middle of the figure. You would not be able to see that from the outside. If I picked the midpoint of one of the sides here and drew this red segment coming down, that, you know what, I shouldn't have done that in red. Let me do that in purple instead. This segment then that goes from here to here, there we go, that is what we call the slant height of a pyramid. And that measurement is going to be important a little bit later on. And I don't know if this is important or not, but I'll put this in here as well. What we have here in black, guys, that was part of the original figure right there, that is what we call a lateral edge in a pyramid. Now, there are four of them here, and I'm just going to highlight the one of them in that spot right over there. But learning the difference between a height or an altitude, and those mean the same thing, and a slant height and a lateral edge is going to become really important pretty soon when we start finding surface area and volume of pyramids. Okay, we'll go much faster through the rest of this. A triangular pyramid, let me get back to one other idea. Let me go back to green here a second ago. The interesting thing about pyramids then is that all of the sides, like this guy right over here, I guess I hit a crayon right there. Gotcha. All right, is that we are dealing with triangles for the sides of our pyramid. Now, a triangular pyramid is interesting because the base is a triangle, but then so are the sides as well. So if I was going to draw a triangular pyramid, I'd probably draw something that looks like this, and then I would connect those last 2 points with a dotted line. So there's my triangular base, and then I just pick a point somewhere up above it here. That point right there I am going to call the vertex of my pyramid, and then I'll draw the three lateral edges. There's going to be one of them. Here is a second one, and you'd be able to see all three of them here. There's the third one. So the base of a triangular pyramid is a triangle. That's what the adjective in front of the word pyramid means. All right, and that's what we've got right there for a triangular pyramid. For an octagonal pyramid, as you might guess, we'd start with a base that's an octagon. I'm going to draw this one upside down. Now, again, this gets a little bit weird here, guys. 1, 2, 3, 4, 5, 6, 7, 8 sides. Whew. So you might want to make that really, really clear where those vertices are in an octagon right there. Okay, so it looks something like that. And now I just need to come up with a vertex, which I'm going to put down here on the bottom of the figure. Okay, and now we're just going to draw all the lateral edges that you can see. So on the front of the figure, it'll go here and here, and I think you'd be able to see this one and that one. I think those four would be visible, but this fifth one right here would be hidden. So would this one right there, and this one right there, and this one right there. It's a little bit tough to see, but there we go. Guys, that's an octagonal pyramid. This one is just upside down. The base is the octagon. That's what the name tells us right there. So your base would be right here in blue, and the vertex of this pyramid is now down on the bottom. So drawing these things can definitely be a little bit weird, everybody, but hopefully we'll get the hang of it pretty quickly. Now there is one other idea that I want to throw at you guys that this textbook doesn't cover, but our old math books all did, and I think this is really neat. This is called Euler's theorem. Everybody wants to pronounce this name Euler, but it's actually Euler. He was a really famous Swiss mathematician, lived I think in the 1800s. I'm not certain about that. And in Algebra 2 next year, you guys will learn a lot about Euler's number. Not so much about the guy himself, but he came up with a number that's really, really important in math, and they named it after him. It's just E, and kind of like pi, it's an irrational number that goes on forever. But here we go. Euler's theorem said the following: that in any polyhedron that you are dealing with, this formula holds. F plus V is equal to E plus 2. And what that stands for, guys, is our number of faces, there's the F, plus the number of vertices, that's the V right there, is always equal to the number of edges, there's the E, plus 2. And just to go a little bit further with that, we haven't really used those words all that much here yet today, but if we talk about the basic concepts of geometry, the vertices, everybody, are basically, you know what, let me do this in black. The vertices in a polyhedron are essentially the points where different things come together. Edges are going to be the lines that you're going to draw. And faces, this is a flat two-dimensional object, that is planes. So these are actually the very first three things that we talked about in geometry way back in the beginning of the year in August. Points, lines, and planes are kind of the three building blocks that everything is based on. Well, Euler put together, and then it's a theorem, not a postulate, because he proved it to be true, that in any polyhedron, the number of faces plus vertices is always equal to the number of edges plus 2. Let's see that in action here, everybody. Now, if these three figures look familiar, I stole them from the first slide right here. That's what we were talking about right here. So I just copied and pasted these. Let's take a look at what we have going on right here. So the first one we're dealing with is they have listed as a tetrahedron. But what we're dealing with here, I hope we can see it, is a pyramid, not a prism. And the base of that pyramid has three sides to it right there. So the name of this figure right here is a triangular pyramid. That's what we're dealing with. And let's see if we can't count faces, vertices, and edges and put them all together. Okay, I actually want to start with vertices because I always think that's probably the easiest. Vertices, we said just a second ago, right here, are the points in this figure. So let's count points. My base is a triangle, so I have 1, 2, 3 vertices on my base, plus another vertex up here at top. That's it. So we've got 4 vertices in this figure. The next one I want to do is count edges. And the edges, we said right here, edges are the lines that we use to actually draw this figure. So I'm going to go with, let me go to red right here, edges. A triangular base is made up of 1, 2, and 3 edges right there. And then we also have edges going up to the top. 4, here's 5, and here's 6. So it looks like we have a grand total of 6 edges that are in that figure so far. Now, faces. This can get a little bit tricky. These are the flat planes that make up your pyramid, and this can be a little bit hard to count, so let me get rid of all the drawing that I did there, and let's talk about faces, everybody. I'm going to switch to purple for this one right over here. Okay, a pyramid, we said, has one base, and this one is a triangle, so the bottom of this figure is one face. Okay, we've got that. Then, this pyramid is made up of triangles that go up. So here's one triangle right there, so that's now a second face. A third one is this triangle right here on the front, and then, this gets messy, guys, there's another triangle that's on the back of this figure right here that looks something like that. So this tetrahedron has one triangle on the bottom and 3 that go up on the side for a grand total of 4 faces. Now, Euler's theorem said that F plus V should equal E plus 2. Let me write that down. F plus V should equal E plus 2. Well, in this figure, F was 4, V was 4 as well, E was 6, and we should always add 2 to that. Well, 4 plus 4 is going to get us 8. 6 plus 2 gets us 8 as well. So it works in this first example. Let's move on to a cube here, guys. All right, and I'm hoping this one's a little bit easier. Faces. When you throw a die, there's 6 possible outcomes. There's a bottom and a top, a front and back, and a left and right. So this figure has 6 faces. Vertices, there are 1, 2, 3, 4 of them on the bottom of this figure, and likewise, another 4 vertices up here on the top. 4 plus 4 means we're going to have 8 vertices. Now, edges. How many lines do we have to draw to create this cube? Work your way bottom top. The bottom is 1, 2, 3, 4 edges there. The top is also 1, 2, 3, 4 edges. And connecting the two, 1, 2, 3, 4 edges run vertically to connect. So 4 on the top. 4 on the bottom, 4 on the top, and then 4 running vertically means we have a grand total of 12 edges. And let's see if this works now, guys. Faces plus vertices, 6 plus 8, should equal edges, 12 plus 2. Does it work? 6 and 8 is 14. 12 and 2 is 14 as well. And so that kind of tells me then that this seems to work in this case right here as well. 14 equals 14. And in your octahedron right there, okay, we basically have 2 square pyramids kind of fused together. So faces, there are 4 of those triangles on top and another 4 on the bottom. There are 8 total faces in an octahedron. Vertices, points now, 1, 2, 3, 4, a vertex up on the top and a vertex down here on the bottom. That looks like 6 vertices there. As far as edges go, there's a square in the middle that has 1, 2, 3, 4 edges. Then running up to the top, 1, 2, 3, 4. So another 4 on top and another 4 on bottom. So 4, 4, and 4 makes 12 edges there. And sure enough, 8 plus 6 should equal 12 plus 2, 14 equals 14. So doing 3 examples isn't a proof, but it kind of looks like Euler's theorem works, at least for these 3 things that we've talked about. Guys, that was all I wanted to give you in 11.4a, just kind of an introduction to the vocabulary of 3-dimensional solids, and then we'll come back with our next video on 11.4b and talk about how to use that to actually find the surface area of some of these polyhedra. All right, guys, thanks and good luck.